Yeah, I think so. Chapter 11 is on intermolecular forces. Intermolecular forces, right now, balls up here when you're ready. Intermolecular forces is the sticky stuff between the molecules. So take your two hands. The intermolecular force is your thumb part. So not the bonds in the molecule, in between the molecules. So let's point out my perfect star. So if a star was a molecule and a square was a molecule, we're talking about the stuff in between that holds them together. Not the line. Not the bond. Okay? So when I keep saying intermolecular force, I'm talking about like on the outsides, not on the insides, okay? There are 4 different types of intermolecular forces. 1, 2, 3, 4. Hey, Drew, I feel like we shouldn't set that up. So we're just, because I don't know what's going to happen. Things are changing really fast.
Oh, yeah. Let's go.
And it's not till next week anyways.
Okay.
Just leave it. All right. Oops. I'm going to actually write it out. The first type is called London dispersion. Sometimes it's named after a dead white guy. His name is Van der Waals. But for us in our textbook in the College Board, they call it London dispersion forces. All molecules, all of them, every single one, has London dispersion. It doesn't matter what it is. They all have London dispersion because they all have electrons. Here is an atom, like a brain eyeballs type atom. They don't really think this. Positive center. If by chance all the electrons were on one side of the atom, because electrons move. They're not things, but their energy moves. That means that this side of the atom has a teensy or even big partial negative charge. Here's our next door neighbor. They also have that situation going on. The side that doesn't have the negatives then would be positive. That's the London dispersion intermolecular force. Intermolecular force is just like a magnet. Positives and negatives, it's in between. Not inside, the inside causes it, but the actual force is in between. The vocab word for that is called polarizability. Polarizability means the electron scooching to one side. If there are lots of them, this can be very strong. The more electrons there are, so like the big guys, like when they have 100 electrons, that's like 100 people on a bus all sitting on one side. It's going to tip the bus. Like 100 people is a lot of people to tip the bus versus like 2 or 3. The more electrons, which just comes from the number, equals greater polarizability is stronger. Okay? When the music starts, just summarize it, but can you practice using the word polarizability? Ready? Go. Go ahead.
So is polarizability like just like the attraction between them?
The polarizability is the electron scooch to one side. The attraction is the London dispersion force.
Oh.
The polarizability is like the verb. Okay. And this is like the noun. Okay. Dipole, dipole. Dipole-dipole is when you draw the Lewis structure and it has a dipole. So it's asymmetrical. It has a wonky side. It's trigonal pyramidal, like way going back to that stuff. So we're just gonna make a circle because I don't know that all of you can draw stars as good as me, so I'll just do a circle. Just kidding. Obviously. Let's pretend its dipole goes like that. And let's draw another circle because I don't want to pressure you to draw stars as good as me. Like that. This part here, the negative and the positive, is where the dipole-dipole force is. Somebody last hour asked me, where does the name come from? I didn't realize that that wasn't a connection for you automatically. Because it's a dipole and it's a dipole. Dipole, dipole. Okay? No, because it was multiple of them. Okay? Dipole, dipole. This only molecules that when you draw their Lewis structure have a dipole are going to have this. Like everybody has this, but only some of them have this. Bad teaching. This is what you're looking for on the AP exam. Something that has a double bonded oxygen. Okay? It's going to be organic because it's AP Chem and they like to make things trickier than normal. The organics that have this here have dipole-dipole. Okay? That double bonded oxygen makes a wonky molecule, creates a dipole. You're not going to have to like draw where the dipole is. That part is too hard for you, but you have to know that it's a dipole-dipole. Okay? I'm going to go right into H-bond because it's basically the same thing. H-bond stands for hydrogen bond. It's when in a molecule, hydrogen is bonded to oxygen, nitrogen, or fluorine. The intermolecular force is not the bond. But hydrogen's like teeny tiny, and these other guys have really strong electronegativities, so they make like this super strong dipole. The intermolecular force is over here. It's in between them. The dipole is on the bond, but the force is in between. So it'd be like over here, over here, over here. That teaching, what you're looking for is a hydroxide. Remember, hydroxides have the all name propanol, ethanol, butanol. Those are the hydroxides. Those are the H bonds. Okay, when the music starts, can you talk about my two bad teachings? Talk specifically about them, how you can tell. Ready, go. That's definitely what I said. Okay, the last one is called ion dipole. We've actually played this game before, we just didn't call it this. It's how stuff dissolves. It has an ion. Let's do sodium +1. That's called an ion because it has a charge. And its intermolecular force is with something that has a dipole. Like water. Water has a dipole. An ion is an ion, hence ion dipole. The intermolecular force is right here, in between. So this is definitely the square and the star, like two different things. That would be like an ion dipole. Okay, so let's draw the chlorine part. Ion. Dipole. Ion dipole, right right there. Okay? That's how stuff dissolves. These are the beakers that you have to draw them in. So we did that way back in chapter 4, and I'm bringing it back to remind you how to draw them with the water molecules. Sometimes it's like, draw 3 water molecules around them. When the music starts, can you talk about how you know that it's the H part and the O part? How do you know which way to draw? Ready, go. Yeah. This, good thing I said it wrong anyways. The stronger the intermolecular force, the higher the melting point. I'm just going to write MP. If you're not going to remember, write melting point. The higher the boiling point, the more, this might be a new word for you, viscosity is like how goopy it is, like syrup is more viscous than Kool-Aid, like thick. Like glue is more viscous than water. I switched the colors on purpose. The lower the vapor pressure. It's the only one that's opposite. Vapor pressure is how much is evaporating. And if they're held on really tight, they're not really evaporating, so it makes it opposite. BP is boiling point. Viscosity is like goopy. Okay. Flip your paper over because we're going to do a page on the back. That was chapter 11. Let's learn chapter 13. No. Crystalline solids. I know I told you today was extreme teaching. I'll fill in the details. I will, yeah. Have faith. This is so like I can be like, hey, pull out your math, and then we can answer questions.
Can we like FaceTiming or like
On the record. 4 different types of crystalline solids. How'd it go? The first type, I wanted to remember. Metallic. Is metallic. Thank you. Then ionic. Then something we've never heard of before, covalent network. And the last one is molecular. Metallic crystalline solids are metals only. We fight this in our head because if I said, I just gave you iron, I'm like, what type of bond is it? You in your head might think there isn't a bond, it's all by itself. But it's bonded to like a gazillion other iron atoms, right? So we talked about how they were like the communists, that they all kind of shared their electrons. The real words for that are the electron C model. Remember, that's how come they can conduct electricity, because their electrons are free to move, it's malleability, all of that kind of stuff. Okay, ionic is going to be a metal and a non-metal. To the left, to the right. You guys, to figure out strength for these, it's called lattice energy. We have done this, but just bringing it back. Lattice energy is going to be your charges. We call them Q1, Q2. It's just the charges, so like +1, -2 over the distance. But now we know a lot about distance. We know a lot about radius. That distance comes from the radius. So like energy level 4 is going to be a greater distance than energy level 2. Okay, so that's kind of how it's going to squeeze in together. So the higher the charges, the stronger. Shorter distance, I'm going to write like low N. N is the energy level. The little guys also are stronger because they're real close together. Okay, new category. Such bad teaching. Covalent network. It's either going to be germanium, silicon dioxide, SiO2, quartz, or diamond. Those are really like the only real life examples of covalent network, and they're super into real life examples. So it's going to be one of those. What it is instead of intermolecular forces, so they don't even play a London dispersion game. The word they are going to use is interlocking. Covalent bonds. So you're looking for germanium, you're looking for silicon dioxide, diamond, or quartz, and you're looking for the word that says interlocking. Okay? These are like the strongest of all time. Think about a diamond. These have the highest everything. Highest melting point, highest boiling point. Like it cannot melt a diamond. If you kind of just like keep diamond in the back of your mind, that's why they make countertops out of quartz. You can put like hot stuff, like nothing will ever happen to it. They don't do anything. They're very pretty and expensive. Okay. And the last one is molecular, is when we have all nonmetals. Organics, the carbons, the hydrogens, the oxygens, those are all nonmetals. Nonmetals are over here. They're called molecular. Okay. When the music starts, can you just go through those 4 categories, and then we'll learn chapter 13. Okay, ready? That was chapter 12. Let's do chapter 13. Chapter 13 is on solubility. The solubility math is going to be your molarity equals moles divided by liters. Just reminding you of M1V1 equals M2V2 right now. Although on our Cume test, perfect. We remembered, we're fine. Okay. Solubility is a synonym for dissolving, okay? We talked about it when we talked about KSP. How do we know if something dissolves like dissolves like? Water is polar. Polar is a synonym for has a dipole. Has a dipole means I draw the Lewis structure and I have an arrow on it. Like an overall dipole. Like it's wonky, it's not symmetrical. Will dissolve other polar. So I draw the Lewis structure and it has a dipole. Or it can, it can dissolve ionic stuff. That makes sense. Salt water. All of that stuff dissolves. Bad teaching. Carbon tetrachloride is the other example. Is non-polar. It's tetrahedral, like it doesn't have a dipole on it. That means no dipole. Will dissolve other non-polar talk about solubility, and then we're going to do some sample problems to kind of tie it in and show what you need. Ready, go.
The sun goes down, the stars come up.
Are in the back of the PowerPoint that I did not go through. So can you find them? Keep your map on next to you. So the first question says, what are the intermolecular forces for the following molecules? We have 4 options. London dispersion, dipole-dipole, H-bond, or ion-dipole. The answer is always going to be at least London dispersion because all molecules have London dispersion because all molecules have electrons. The electrons cause the polarizability. They all just scooch to one side. That creates like a temporary dipole, and always, they're all going to have them. Okay, so my next category is dipole-dipole. That's if it has a dipole. So for now, I'm going to go ahead and draw this Lewis structure because maybe you remember them, maybe you don't. But that's just straight tetrahedral, so those don't have a dipole. So no dipole-dipole. An H-bond has to be with oxygen, nitrogen, or fluorine, so none of that. And an ion dipole has to be like a square and a star. Like it has to have an ion and something with a dipole. Like it'll be like 2 things, 2 different things. It'll be like NaCl in water or something, okay? So this is London dispersion only. Does that make sense in your head? Okay. CH3 or CHCl3. If you can't see it in your brain eyeballs, that's going to have a dipole. It's asymmetrical. So I know it's dipole-dipole. I'm going to just double check to make sure it's not an H bond, and it's not because it has to be oxygen, nitrogen, or fluorine. NH3. I'm drawing it like this on purpose. NH3 adds to 8. But 8 makes it have that trigonal pyramidal shape, so that's a little wonky. So this is going to have a dipole, but it has that H bond type of dipole. If you write dipole-dipole as an H bond, you're not wrong. Okay? So I probably, if I were you, I would err on writing them all. It is a dipole. It's just a special type of dipole called the H bond. I think it just depends on the rubric and the reader if they expect you to do both. Okay? Let's look at like organics. So can you scooch down here because this is most good for you. I know. Remember? Or is this like PTSD? I don't know. PTSD. Okay. Methane is 1, butane is 4, hexane is 6, octane is 8. But they're all tetrahedrals, so all of these are no dipole. Because tetrahedrals don't have a dipole. So all of these are London dispersion only. But remember, London dispersion can be super strong. Like if I put 200 kids on a bus and we all sat on one side, we could tip the bus, okay? So even if it's just London dispersion, doesn't mean it can't be strong. So look at the boiling points, -164 to 128. Their boiling points are going up because the London dispersion polarizability is also going up because there's more electrons. The more electrons, greater polarizability, higher force, higher melting point, boiling point, viscosity. I'll have you talk about it in a second. Let's do this one though. Hexane to hexanone, double bonded oxygen means a dipole. To hexanol means an H bond. So you can see the boiling point goes up, 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 because stronger, stronger, stronger. Okay, when the music starts, can you talk about London dispersion forces, use the word polarizability, and then just make sure your bad buddy gets how to pick out double bonded oxygen. Okay, but now rank them. Which one would?
The lowest, the highest one.
Yeah. So which one would have the lowest, and which one would have the highest? Lowest would be lead and dispersion only because they're all the same size. It's all the same kids on the bus. Not like methane to octane. Those were all different sizes. So lowest, then we have our dipole, then our H bond. And then look at this guy has 3. So that one's the strongest. This is some math that we will do at a different day. Let's look at number 8. Number 8 is our crystalline solids. You might want to flip your sheet over. We have 4 options for crystalline solids. We have metallic if it's a metal. We have ionic if it's a metal and a non-metal. We have covalent network if it's germanium, silicon dioxide, diamond, or quartz. And then we have our molecular, which is really anything organic, everything on that metals. So germanium, what is that going to be? It has the highest everything. It has the strongest everything. It does not melt. Glycerol, those are all non-metals. It's an organic-y thing. How do I know it's an organic-y thing? Because it's a bunch of carbons. Anything all non-metal is called molecular. That means they're all to the right of the staircase. Metal and non-metal. What is D? That's an organic-y thing. Molecular. Okay, but then what's the question? Which of the above compounds will most likely be a solid? Solid means strongest. They're stuck. Germanium. Okay. Okay, it was close. It had G in it. Predict whether the substance is more likely to dissolve in carbon tetrachloride or water. It's like I gave you those options. Water is only going to dissolve other polar things. That means they have a dipole. Carbon tetrachloride is only going to dissolve things that don't have a dipole. Heptane is just 7 tetrahedrals in a row, if you remember your organic. So no dipole. So which one? Carbon tetrachloride or water? That was also bad teaching. I should have let you talk about it. Sodium sulfate, metal and non-metal. That's ionic. Let's look at our notes. Ionics are for which one? Water, because it's polar. Polar means it has a dipole. Hydrochloric has a dipole. It's linear, but it's not the same. So if it has a dipole, we say that's polar, like dissolves like. Do you get it? You know what? Iodine is going to be this, and that's not going to have a dipole. It's symmetrical. So that's going to be no dipole, and that's carbon tetrachloride. Okay, let's look at big organic guys, though. Which would be most soluble in water? That means the most polar, the most sticky spots, the most dipoles, which would be least likely. So things I'm looking for. Oh, I see a hydroxide. Oh, I see 2 hydroxides. Oh, I see a chlorine. Oh, I see a hydroxide. This has a lot of electrons. So this has a lot of polarizability. Plus 2 H bonds That's a lot of like sticky things. That's like all these electrons are doing the polarizability thing. That's a strong London dispersion and 2H5. This is the most going on. That would be the most. Do you see how this one is going to be London dispersion only? It doesn't have a hydroxide. It doesn't have a double bonded oxygen. It doesn't have anything. It does have good polarizability, though. It's kind of big. This is little polarizability and plus an H bond. That chlorine makes a dipole. I know it's not a double bonded oxygen, but it's like a wonky guy. So it would have like a, they don't have the same electronegativeness here. I'm not going to draw it all out, but it's this. Do you see it? Okay. This is all London dispersion. Are you looking at the wrong one? This is H bond. Okay.
Is there a question? I'm not going to the bottom. You say you can know what they mean?
That's like the question. Okay, in your worksheet packets, oh, here. In your worksheet packet, mine's blue, I know yours is in blue, to practice your intermolecular forces, the first piece of paper. Obviously, none of them are labeled or have titles because the first piece of paper in that worksheet packet for your homework. Hopefully I see you on Monday, but if I don't, because things are changing, you need to take all of your paper home. Because when we're Facebook, YouTube Live, and be like, hey, get out your math, get out your worksheet.